Okay. Now, we can all thank Alexis for the quiz. She bailed on class today. Who else is missing? Oh, Tim. I had lunch with Tim. Where is he? Okay, hold on. You could really blame Tim. At least Alexis told me that she's not feeling well. It's like, I mean, I didn't think she was sick enough not to come to class, but at least she did. I mean, I literally had lunch with him an hour, 45 minutes ago. Oh, that's hilarious. All right, so let's solve this problem real quick. Let's get rid of all this. Oh my gosh. Am I going to need any of the binary tree stuff for the homework?
Yeah. Mm-hmm.
Oh, okay. Okay, so what do we call this guy? Oh, so we're going to do define sum n list to be a lambda that's going to take an n list as a parameter. We're going to have our normal pattern. So if null n list boil down to 0, because we're summing some stuff up, right? Otherwise, what we're looking at for the car of the n list is either going to be a number or another list. So you can choose your poison as to which predicate do you want to use. Do you want to ask if it's a number or do you want to ask if it's a list? So we'll say if number car n list, if that guy's a number, then what are we going to do? We're going to add car of n list onto sum n list quarter of n list. Right? Else, we're going to add, must be a list is the first element. So we're going to add whatever is returned for sum n list on the car of n list to sum n list for the cooter of n list. Like that. All right, how many people got it? Ish? How many people like horribly, horribly disfigured it? like probably going to get a 30 disfigured or looked like you had parentheses disfigured. Okay. Okay, so you wrote a non-working helper function. All right. Oh, speaking of which, did you get my invite to that Slack channel?
Yeah.
Okay. Because I have a couple ideas I'm going to pitch in there. I just wanted to make sure. Do you happen to know do you know Michael Thalheim? Does anybody know Michael? Do you know what his Slack name is? I found 2 Michaels on there. One was just Michael. Okay, the other one was not Michael Thalheim. So I went with just Michael. So we'll see if it's the right Michael. But in any case. Okay, questions about this question. So this is pretty similar to the last quiz, right? Last quiz was sum a list of numbers. So this just goes one level deeper. We added an extra if statement for whether or not we had to call a second recursive call for lists within lists. That makes sense? But otherwise, we're pretty much seeing the same pattern we're seeing over and over again. All right, so I mean, I get it. I wouldn't have given you this quiz if I didn't expect, if I thought everybody was just going to like do really, really, really well on it. So I'll try to grade it somewhat reasonably based on, but I want to keep driving this pattern home, or driving this idea home that we have these patterns. And we see the same patterns over and over and over again when we're dealing with recursively specified data. Okay, so let's look at the homework. Was it easy?
I don't know which one you're talking
That seems to be the thing on each assignment, right? There's like one easy one and one hard one. Okay. What questions were there? Oh, right there. Okay, good. Oh, both 3 stars. Which one was the easy one? 34. So we should do that first. Kind of warm up. All right. So 3 stars. Now, interesting question. Before you even start the question, does that intimidate you?
Yeah.
Is it like a scary thing? Like oh my gosh. Kind of like, like if like you don't like horror movies and it's like a rated R horror. Remember do you see the movie Conjuring? When Conjuring came out, that movie was terrifying, first of all. But I remember when it came out, they were like, the critics were like complaining that it was like too over the top, too traumatic for some people. And there was this movie theater in Texas that actually had this sign up warning people about how bad it was, and that they invite people who are disturbed by the movie to schedule an appointment with their priest. So this movie theater hired a priest to meet with moviegoers who, had a problem moving on following the movie. Now, if you see a sign like that, wouldn't that just like adjust your expectations going in? Because based on that, I was very disappointed. I mean, I laughed at parts of that movie, but I realize I'm a broken soul. So it's yeah, it is what it is. Okay, so 3 stars. Write a procedure called path that takes an integer. Oh yeah, this is the left-right turn one we talked about at the end of class. Write a procedure called path that takes an integer n and a binary search tree that contains the integer n and returns a list of lefts and rights showing how to find the node containing n. If n is found in the root, it returns the empty list. Okay, so we're returning a list of directions, kind of GPS directions, if you will. Remind me, when we looked up binary tree, is it less than or equal to on the left? Okay, and then greater than on the right. All right, so let's look at this guy. Okay, so we're going to define path to be a lambda that takes in a number and a binary search tree. So far, so good. All right, so very first thing we're going to, well, we have our pattern here, right? So we're going to say, is our binary search tree empty? If it is, return the empty list. This covers that special case in both cases. So it's if we're looking for a number in an empty tree, this will return the empty list. Otherwise, it'll complete our cons, right? Because we're consing lefts and rights together to do something. So we'll ask that same pattern. So if null BST boil down to the empty list. Otherwise, we have stuff in there. All right. So if we're looking at a binary search tree, if I have a binary search tree, what's the car of that guy going to be? Okay. What will that root look like? What's the format of that? Okay. Is it always an integer? So my binary search tree, here's the root, that's a number. And then this guy right here, that's the left subtree. So that is all numbers less than or equal to the number. Actually, this is the left subtree. That's all numbers less than or equal to 17. Here's the right subtree. Doesn't go all the way down there. I'm not matching the parentheses, but those are all the values greater than. Okay, so we have a number. Now we're searching for that exact number for directions, correct? So we're going to ask the question, if we're in here and we assume that binary search tree is an accurate binary search tree, we know the car will be a number. And we want to know, is that number the value we're looking for? So if equals n and car of BST, if I found the number I'm looking for, we've arrived at our destination. And if we've arrived at our destination, what do? Do we have any more turns to take? No, we're there. And we need to complete the ongoing cons, right? So we're going to boil down to empty list. That finishes off the cons. We've arrived at our destination. Boom, here's my list of lefts and rights. Else, I'm not at my destination. So I need to ask, is the place I'm going less than, well, should it be to the left or should it be to the right? All right. So if the number I'm looking for is less than the value I'm currently looking at, then it's going to be to the left. Now I can ask less than or equal to, but we really know it's not equal to. I wouldn't be here. If it was equal to it, we've already finished. So I can ask if it's less than. But if you did less than or equal to, it's not incorrect. It's just what's called a slight inefficiency. So now we're going to ask the question, if less than n car BST. So if n is less than the car of BST, I think that's the right order, isn't it? I think this says this value less than this value. Okay. So if that's a true statement, if n is smaller than the car of BST, then I need to look at the left child. Correct? So I need to do a couple of things here, right? One thing is I'm going to cons a left on there. What's the other thing I'm going to do? Call path, not on the rest of the list. The left binary search tree. Okay, so I'm going to cons the word left onto whatever's returned by the path of how do I get the left binary search tree? CADR?
Yeah. Well, we created the LSON and RSON.
That's for binary trees. Is that binary search trees or just binary trees?
Binary search trees. Because it just calls the cat or the cat in
Okay.
there.
Yeah, fair enough.
Yeah.
Fair enough. All right, so you want to do LSON of BST? LSON of, yeah, BST. So we'll call path on the same value we're searching for.
Wait, wouldn't that call it with 2Ds though? The LSON?
Oh, that's just the cat.
Yeah, left sun, we wrote it.
The RSON is the car of the cat.
CADR is LSON. CADDR is the right sun. So call path with the same number, passing it the left sun of the tree. That's if it's less than. If it's greater than, cons right onto path n of RSON BST. Like that. Let's go ahead and test this dude. All right, and this dude should give us right, left, left. Oh, hold on. Yeah, here's my right, left, left. This guy down here. It's like, where's reds and stuff coming from? We still had our call up here from last class. All right, make sense? All right, questions on that one? Okay. Next question. 135. Write a procedure called number leaves that takes a bin tree and produces a bin tree like the original, except the contents of the leaves are numbered starting from 0. Okay, so every time we find a leaf, we need to A, keep track of the leaf we found, and B, this is actually going to be interesting. So in this case, the first leaf is this guy. So that's going to be leaf 0. And this is going to be leaf 1. Right? This is leaf 2. This is leaf 3. This is leaf 4. So we needed to keep track of those guys. Now, an issue we're going to run into here, though, is when we have an interior node and we call to the children. So we're at this guy right here, and we know the left child is a leaf. We can ask, is the left child a leaf? If it is, we have a number we can give it. But when we do that, we then need to increment the value for the right child before we give it to the right, regardless of whether the right child is a leaf or not, my current value is one larger than it used to be. Now, a challenge we have here is that we have no variable, I guess we don't have a way of storing values over time. The only way we can store values right now is pass them back in. That's where our helper functions kind of have come in, right? So we have to kind of keep track of that stuff. So number of leaves is going to have to kind of take in a cur number. So we're going to probably have a number leaves helper that will pass in a 0 for our first value and then make the decision whether or not we need to up it before we kind of go down the list. Okay. So define number leaves helper like that. That guy's going to be a lambda that's going to take in just a bin tree and count, right? Or current, yeah, count's good enough. Yep, just takes in a bin tree. So this guy's going to be bin tree and a current count. And let's go ahead and make our initial call to that. Number leaves. It's going to be a lambda that takes in bin tree and then calls number leaves helper, passing it bin tree and a 0. Okay, so now we can come back to this dude. All right, so here's the body of my number leaves helper. So if I am looking at a leaf, so my binary tree comes in 2 forms, right? It's either just a number, correct? Is that a legal binary tree? That's a leaf, okay? So if I'm looking at a leaf, I want to boil down to the current count. Is that an accurate statement? So if leaf bin tree count. Fair enough. Now we need to be careful, make sure we're always passing the right count in. Otherwise, I must be dealing with an interior node. So we need to ask ahead. So if I'm dealing with an interior node, I'm in this else right here, I need to go ahead and take a look at the left and the right side of that interior tree or interior node to find out whether I need to change my value going in. All right, so we have a couple of different options here. If both children are leaves, if the left son and the right son are leaves, my left son is going to get count plus 1. My right son is going to get count plus 2. That's the values I'm going to pass in. Correct? And I also happen to know the amount of recursive calls then. So I don't necessarily need to worry about passing, the future values in. Now, if my left son is a leaf and my right son is not, I'll pass in count plus 1 for the left son. Actually, I think we're passing in just count because it'll be the current value of count. So the previous thing I said would be count and count plus 1 for the 2 leaves. So in this case, we'll say we're going to pass in the count, and then we're going to call number leaves helper on the right son, which is going to be an interior node, and he's going to get count plus 1. All right, so we're passing in the buck, but we have to be careful about asking those questions ahead of time. We need to know how we need to throw our numbers in there. Okay? So let's ask the most exclusive situation first, where they are both leaves. We also know this will be the end of the road. So I want to ask the question if my left son is a leaf and my right son is a leaf. So if I'm in this else here, that means I know that the binary tree I'm currently working with is an interior node. Therefore, I'm going to ask the question, if leaf else on bin tree and leaf arson bin tree, if both of those dudes are leaves, then what am I going to do? Remember, we're still building out a tree. If we look here at, well, we're building out a tree-like structure. So we look back here, my output is going to be the list containing my value, whatever that guy's called. Is it number at or something? We have arson, elson, and what's the other? Contents of. That's okay. So I'm going to create a list out of contents of and whatever's returned by number of leaves on, and I'll pass it the number, the elson, and the number of leaves for arson. And up here, we already done the count. This guy is not just count. I just saw in our output here. Our output says create a list from, is this the right question? This is the right question. So I need, when I have a, oh yeah, it is. I was looking, we had leaf here. I get it. So yeah, we just boil down to the number, That's fine. So that's why we just have count here. Here's going to say if both the left and the right are leaves, then we're going to go ahead and we're going to, what does my output look like? I'm going to build a list out of the contents of, as well as whatever's returned on the left side and whatever's returned on the right side, passing it the correct count. So one's going to be count, the other one's going to be plus count plus 1. And we know we're at the end of the thing. So we're going to go ahead and we are going to create a list out of contents of, like that, bin tree, along with whatever number leaves helper returns, passing it the elson of my bin tree, and passing it the current value of count. And let me go ahead, I'm going to kick this down. And I'm also going to then call number leaves helper, passing it the arson of bin tree and plus 1 count, or plus count 1, you can choose. All right. That's what we do if both the left and right are leaves. Now, if only one of them is a leaf, we'll pass our count to that one, and then we'll pass count plus 1 to the other one. If leaf elson bin tree. Now I know if I'm in this else here, that is the else to this and. If I'm in there, I know that both of them are not leaves. At most, one of them is a leaf. Okay? So if the left guy is a leaf, then I'm going to go ahead and I'm going to create a list out of contents of bin tree, number leaves helper, elson, bin tree, and count, number leaves helper, arson, bin tree, plus 1 count. Now, right off the bat, something we should notice here is these are the same. We have a duplicate pattern here, don't we? We've called num leaves helper on the left and the right, passing a count and plus 1 count. So we're gonna come back and we're gonna adjust this. We're gonna say, does this guy need to be an and, or could it be an or? But now we're gonna see the alternate side. If the left tree wasn't a leaf, does that mean that the right tree must be a leaf? Or is the right tree still just maybe a leaf? Still just maybe a leaf, right? So we'll ask the question, if leaf arse on a bin tree, if that guy's a leaf, what are we going to do? We're going to create a list containing the contents of bin tree along with number, leaves, helper, else on bin tree plus 1 count, because I know that guy is not a leaf, but I know the other guy is. So I need to go ahead and bump my count, proactively here for the left side. And then number, leaves, helper, arse on bin tree, count. Else. If I'm in the else here, I know that they're not both leaves. I know that the left side is not a leaf. I know that the right side is not a leaf. So that means that none of them are leaves. And if none of them are leaves, what do we do? Well, what's the most straightforward thing we would do? Pass count to both sides and hope for the best? As far as I know, the right and the left, so if we come back here to our example here, here's our interior node, here's the contents of. The left side is not a leaf, the right side is not a leaf. So what are we going to do? We're going to pass. Now we see that this is the first leaf we run into, correct? And we see that this is the next leaf we run into. So we're going to get our 1 and 2, or 0 and 1 there. But if I call interior node here at the same time as I call interior node here, the same value of count, aren't I in trouble? If I pass in a 0 to my helper for this guy, and I pass in a 0 to my helper for this guy, I'm going to get 0, 1, and then I'm going to get a 0 here, which is not what I want. That guy was supposed to be a 2. How am I going to account for that? Go ahead.
How I did it was you just count how many nodes or how many leaf nodes are in the left side, and then add that to the count and pass it to the right.
Okay, so you can pre-process the list,
Yeah,
right?
Just another helper.
Yep. So we can zip through the list and find out how many leaf nodes are going to be on the left, so we can get that value and know how much we're going to have to tack on to the right. Okay, that's not a horrible. That's certainly a straightforward solution. What else could we do? Any tricks we can do here? Anybody else do it a different way? We got to think about how recursive calls are happening. Well, we'll go back here with this one. I am definitely going to be calling my helper function on this left half first. So if I have some way of getting me that number back, the current value of count back, before I make my second call, that would be beneficial. Right? Okay. In fact, you're doing something along those lines by calling that helper and maybe passing that in as the count. So rather than just passing in count, you're wrapping count with count left or count leaves in a binary tree, and it's going through and just giving you a full count. So he's doing something like this. Define count leaves to be a lambda it takes in a bin tree, and yeah. So all this guy's going to do is he's going to ask if leaf bin tree boil down to 1, else plus count leaves else on bin tree and count leaves arson of bin tree. Right? When we hit the end of the road here, if we're dealing with a leaf, tack on a 1. Found 1. Right? Otherwise, go ahead and add whatever count leaves returns for the left son and whatever count leaves returns for the right son. And that should give us the total number of leaves in this bin tree. Fair enough? So then down here, when we call our number of, are we in the leaf contents of, number of leaves helper. So this is the and, this is the left guy is a leaf. This is the right guy is a leaf. That takes us to there. Here's our else. So otherwise, neither of them are leaves. So what are we going to do? We're going to say, create a list out of contents of bin tree, calling number leaves helper else on bin tree, and we'll go ahead and pass in the count on that side. Right? As far as we know, that's what it should be. Now on the other side though, number leaves helper passing at the arson of bin tree, we're going to pass in the what I call it, num leaves or number leaves? Count neither. Count leaves of else on bin tree onto count. Something like that. So let's test this, and then we'll see if we can compress this a little bit.
That last list needs a T in contents.
Contents of...
Contents.
Oh, contents. Almost my first syntax error. Been terrible. All right. So let's go ahead and test this guy. Cool. Is this a botched input again? Yeah. So that's the left child. All right, that is the left child of that. I need to fix these single quotes too, but let's just get the parentheses in. It's the left, that's the right, that's the right, that's the whole thing. Interior node expects 3 arguments. What did I give it? Oh, that's in my, I don't think my input's correct yet. Interior node, here's 1 argument. Here's the second, oh. That's my left node. That's my right node. So this interior node takes in 3 arguments. The first argument is that dude. The second argument is that dude. This ends our first interior node, and this ends the function call. So foo 0, 1, then 2, then 3, 4. Right output. Right. So now we go back in up here just quickly. We'll talk about this since we're short on time here. We probably could compress. We could, well, I don't know that makes it look any nicer, but we probably could do something with this and here and this guy right here, the left-hand side. Go ahead.
Can you just leave one of the ifs and just stick the other if in there twice? Or if true, then else?
Well, okay, so this would be my first question. Is there any difference on what we do between having both of them are leaves versus just the left-hand side as a leaf? There was no difference in our action. So didn't we actually have to just ask if the left hand was a leaf? If they're both leaves, fine. But our action was the same. So we actually could reduce. I actually still think this is the better way of writing it initially. Because now you're handling each specific case. Who cares we have an extra if statement? Scary anyways, right? But realistically, because our action in both of these guys is identical, the lowest common denominator among the two of them is that the left subtree is a leaf. Otherwise, we do a little bit of a curveball here on the right, so that's still its own if statement. And then we have the other element of this. Now, what would be handy? What would be handy here for writing this, let's call it better? Especially this last else, where we had to go and count some leaves, which is going to take some processing power and stuff like that. We're really missing. We go back to, I've mentioned, when we first learned programming, we learned this idea that all languages provide a way of memory, way of asking questions, and a right way of doing repetition, right? Well, we have a top-level way of doing memory with this define function. We really don't have a way of creating local variables. And we're starting to kind of feel that as being a hindrance to us at this point, right? We're going to play these tricks and do things. So we're going to be pretty soon looking at something called a let. All right, and a let allows us to create an internal environment. All right, let's look at the next questions here. Gee. That's the last one for the chapter, so you only get one question? All right. One question for, what's today? Today's Wednesday? One question for Friday, just 1.36. And then we're actually, so now we should be pretty good at scheme by now, right? Or at least know if we suck at it, right? We've been exposed enough to scheme that, so what we're going to start bumping into now is actually looking at some language structures. But then you're going to start seeing that we've actually been looking at language structures all along. Hopefully this was a little bit of evidence right here. We noticed a giant hole in our language. We can't have local variables. All right, I will see everybody on Friday, 1.36. Also, your this week's Bible verse is up. Who? Oh, I had to steer clear of that guy. How do you link that to technology?
We'll find a way.
Yeah.